All right, welcome everybody. Let us discuss the WebAssign from section 11.8 on power series. So when I think of a power series, it is essentially a function which is in the form of a series. That's one way to think about it. Plug in different x's, you get out different series. And a major question here is, for what x's that you plug in is the series that comes out convergent? And so taking a look at any power series, when you want to compute the radius of convergence, the conventional method is to apply the ratio test. One reason why we like the ratio test is because we've got these exponential bits here, like x to the n, that's an exponential expression, and the ratio test tends to work well with exponential expressions. So what do? We take the expression from the ratio test. We take this term, replacing n with n plus 1, put that in the numerator. We take this term replacing n with n, essentially copying exactly what it is, put that in the denominator, that's a double-decker fraction. We take the absolute value and take a limit as n goes to infinity. Then we solve that to be less than 1. And in the process of solving that, one of the factors that results is a factor of x, because we'll have x to the n plus 1 upstairs and x to the n downstairs. We'll take that factor of x and factor it out of our limit, because our limit is as n goes to infinity, and x has nothing to do with n. And when we take that x away, then there is a resulting limit that is adjacent to that x that we haven't factored out. That resulting limit will evaluate to some number. We're going to divide that number from both sides of our inequality, and we will get absolute x is less than that number. That number that we've now divided away, I guess the number that's on the left would be whatever it is, divided to the other side, you have the reciprocal. But you'll have an expression form absolute x is less than something. That something on the right-hand side is your radius of convergence. And so r here is what you solve for in that instance. And to find the interval of convergence, now we're going to have to take whatever the radius of convergence is. In this case, I believe the radius of convergence will be 1. And now, looking at the series, which is centered at 0 because we just have an x here. Later on, maybe we have things other than x. Yeah, here, like now this power series is centered at 13 because x equals 13 is what would sort of zero out that term. But if we have a power series that's centered at 0, well, our interval of convergence is going to be 1 unit on either side of 0. 1 because of the radius of convergence being 1 here. And then what do we do from there? Well, we have to test the endpoints because maybe both endpoints are included. Maybe only one of the endpoints are included. Well, the thing is, when you plug in x equals minus 1 here, the minus 1 to the n and the minus 1 to the n there will neutralize each other because 2 factors of minus 1 make just 1. And then you have 1 over cube root of n. That's a p-series. Now, whenever you assess the convergence of the series at its endpoints, you will never use the ratio test. You already milked every bit of what you could from the ratio test by getting the radius of convergence. In fact, the points at the endpoints are the very points where the ratio test would evaluate to be 1 and is inconclusive. So you're going to have to use some other test. And as we saw here, when you plug in x equals 1, we'll have a p-series. When you plug in x equals, when you plug in x equals minus 1, you get a p-series. When you plug in x equals 1, you will get, in fact, an alternating series, because the 1 times the minus 1 will just leave the minus 1, and the minus 1 to the n upstairs gives you an alternating series. And so at x equals minus 1, we would use the alternating series test. And so I believe, when all the dust settles, the alternating series at x equals 1 will converge, but the p-series at x equals minus 1 will not converge. And so I believe the interval that we're looking for here is going to be between minus 1 and 1, including 1, but not including minus 1. And so this kind of game we're going to play essentially in every single one of these examples. Use the ratio test, solve for that absolute x, or in general, absolute x minus a less than some number. The number that we get on the other side is going to be our radius of convergence. And then we test the endpoints that are as many units away from the center as the radius in both directions, using tests other than the ratio test to know what's going on there. Okay, so that's a lot of preamble, but let's now go to the next example. Here, similar story. Use the ratio test. Replace n with n plus 1, put it in the numerator. Replace n with n, just rewrite the thing, put it in the denominator. Double-decker fraction, that's fine. Whenever you keep, change, flip, and deal with all of the cancellation, one of the factors that you're going to have is a factor of x. absolute value of x at that point. In fact, factor out the absolute value of x, and then evaluate the rest of the limit. Take what evaluates from that limit and divide it from an inequality set less than 1, because we want the ratio test less than 1 to show convergence. And then you'll have something of the form absolute x is less than some number. That number on the right-hand side is going to be your radius of convergence. Here, if I am not mistaken, your radius of convergence will be 9. And so what that means is your interval of convergence goes 9 units on either side of 0. 0 because we don't have x minus 2 where we'd be centered at 2, or we don't have x plus 4 where we'd be centered at minus 4. We just have x. We're centered at 0 here. So our interval of convergence goes from minus 9 to 9. Now, what about minus 9? What about 9? Well, hey, you're going to have to plug in to find out. Plug in x equals minus 9. Hey, the minus 9 upstairs and the 9 downstairs will cancel to leave you just a minus 1 upstairs, and minus 1 to the n, that is, and you have an alternating series. Does that alternating series converge? In fact, no, because the power of n is upstairs, and so you'll get divergence at x equals minus 9. Plug in x equals 9. The 9 to the n and the 9 to the n will cancel, and then you'll just be summing up n, but summing up n will diverge as well. So here, neither endpoint is going to be included. What about this one? Similar story. Run the ratio test. Take this expression, plug in n plus 1 for n, put it upstairs. Plug in n for n, just carbon copy it, put it downstairs. We're taking the limit as n goes to infinity. When you keep change flip and you cancel factors, there is going to be a factor of x that you can factor out. When you factor out that factor of x, there will be a remaining limit. You're going to figure out what that number is, and then you're going to divide that number from an inequality less than 1. Why less than 1? Because we want the limit associated with the ratio test to be less than 1 to guarantee convergence. When all the dust settles, you have something of the form absolute value of x is less than 1. I believe the 1 here, absolute value, that was a Freudian slip. Absolute value of x is less than r. The number that's on the other side, that radius of convergence, in this case, will be 1. And so this interval goes between minus 1 and 1. Now, do the endpoints get included or not? Well, that is going to be determined by plugging in the x equals minus 1 and x equals 1 at the two endpoints. Literally plug in x equals minus 1. The minus 1 to the n and the minus 1 to the n will multiply to be just 1. Upstairs, then, you'll just have a 1. Downstairs, you'll have n to the 8th. That's a p-series. That converges because p is bigger than 1. And so minus 1 will necessarily be included in the interval of convergence. Go to 1. When you plug in x equals 1, the 1 to the n is just 1. So you have an alternating series in that case. And I believe by the alternating series test criteria, you'll get convergence there too. So here we would include both endpoints. What about the next one? Okay, so now we've got another power series centered at 0 because of this x, but yet we're going to go through the whole process. So this one might have even been better to be the first one because it's going to walk you through the process. You're going to apply the ratio test, replace n with n plus 1, put it upstairs. Replace n with n, just carbon copy downstairs. Keep change flip, cancel all the factors appropriately. Then you're going to factor out an x. Then you're going to take that limit and see what it evaluates to, and then divide by it. And divide by it, I say divide by it because you're going to set up an inequality with that limit less than 1, that limit being the limit from the ratio test less than 1 so that you get convergence. And whenever all the dust settles, you have something in the form absolute x is less than some number. And I believe, in this case, since you would be dividing by 0, you will get absolute x is less than infinity, which is a weird thing to say, but it's true. The radius of convergence here is going to be infinite, which is, well, kind of fun to think about. That essentially means that the power series is convergent between minus infinity and positive infinity. It's convergent for any x, which is, yeah, a truly remarkable situation, and yeah, the main emphasis of this exercise. So here's another exercise. This also would have been nice to be at the beginning of the exercise set, but so be it. Here we are. What's nice about this example is this is not just x to the n, but x minus 13 to the n. So the x minus 13 to the n is an indication that this power series is centered at x equals 13. So when you run the ratio test in an inequality less than 1, and you solve for something, now instead of factoring out an x, you're going to factor out a factor of x minus 13. So when you take that limit and evaluate it and send it to the other side, you'll essentially have an expression of the form absolute x minus 13 is less than some number. I believe in this case, you'll get absolute x minus 13 is less than 1. And so that means your radius of convergence is 1, but now that radius of convergence is centered about x equals 13. So now we're looking at the interval between 12 and 14. Between 12 and 14, the value within this x minus 13 will be no bigger than 1, and that sort of indicative of the radius of convergence in effect. So now, we're looking between 12 and 14, but what about x equals 12? Hey, plug in x equals 12, what happens? You're going to get an alternating series that converges. Plug in x equals 14, what happens? You're going to get a non-alternating series that's basically a p-series. You could run a limit comparison test to get the result there, and I believe you'll get convergence as well. So this should include both endpoints, 12 and 14, and the tutorial exercise should probably walk you through the details. What do we got here? We got 3 examples, each centered at x equals 6. So each of these intervals of convergence are going to be centered at x equals 6. In the first case, I believe your interval of convergence is going to be of width 7. And so that means your interval, if it's centered at 6 and it's 7 units in either direction, is going to go between -1 and 13. Now, if you plug in x equals -1 to test the endpoints, let's see, you're going to get -1 to the end. Hey, that diverges. Plug in x equals 13, the 7 to the ends cancel, and you're just going to be summing up 1 in perpetuity. That diverges as well. So here you're going to include neither endpoint. In this case, now there's an n downstairs that's actually going to be helping us converge. It's not going to actually affect when you run the ratio test. That n is not going to affect the radius of convergence. The radius of convergence is still going to be 7. What it's going to affect is one of your endpoints. I believe here, let's see, if we plug in -1 will give us an alternating series, and we will converge as the alternating harmonic series. So x equals -1 will be included, but when you go over to x equals 13, the 7 to the ends will cancel, and you'll get the harmonic series, which diverges. So x equals 13 is going to be a no-go. Will be between -1 and 13, including -1, but not 13. Now, in the last case, because now we have an additional power of n downstairs, which is helping us converge even more, we will actually include both endpoints, if I'm not mistaken, because now the p-series that results in x equals 13 is going to have a power that's large enough. So a nice thing in this example is you're not centered at 0. You have the same radius every step of the way, but now the endpoint considerations are different in each case. So that's kind of fun. What about this next series? We've got that x plus 5. So here we're centered at x equals -5. When we run this limit, we can evaluate that limit. It's going to include x here. It's going to include a factor of x minus 5. So I would separate the factor of x minus 5 out and just have absolute x minus 5 times some number. Don't know what that number is. Now that number that we get is going to be divided from the other side where there's a -1 and give us our radius of convergence. So this limit is going to be, I believe, x minus 5, absolute value of x minus 5 times 1/5. But then, whenever we divide that 1/5 from the side of an inequality with less than 1, we'll get the radius of convergence here to be 5. So the radius of convergence will be 5. Our center is at x equals -5. And so you put that all together, and your interval is going to extend from -10 to 0. We'll have to plug in x equals -10 to see what happens. There you'll get an alternating series, which will converge. And then when you plug in x equals, what we said -10 and 0. Plug in x equals 0, there you'll get a non-alternating series, which will diverge. And yeah, because 1 over ln n diverges. You could do a limit comparison test to 1 over n, and 1 over ln n is way bigger than 1 over n. Okay, why is my screen paused for whatever reason? I'm not sure what's going on here. Come on, okay, there is it shot back to life. Okay, great. Let's keep going. Next one here, I believe when you run the results on this, you will get through the ratio test a radius of convergence that is 0. And what that means is there's only one x for which this converges, and it's the x that is its center, the x that is x equals 1/5. And so I think you'll only get 1/5 for your interval convergence. The radius of convergence is 0. This is a pathological power series for sure. Right, suppose the series has a radius of convergence of 13, and this series has a radius of convergence of 14. What is the radius of convergence of these? The radius of convergence is going to be the smaller of the two, effectively. So whenever you have coefficients that are sort of added together in a power series, the smaller of the two is going to dictate the radius of convergence. That kind of makes sense if you think about it, because this series is just the sum of the two series. And, well, hey, if this series only converges for 13 units of x, then there's no way that we could plug in something 13.5 units away from 0 in for x and get convergence here. So it's going to be the lesser of the two. Suppose the radius convergence of this series is r, and the radius convergence of that series, what's it going to be? Is that even going to have an effect? Oh, right. Yes, it is. Because you see, when you replace n with n plus 1 here, and you do a ratio test, you're going to be factoring out a factor of x to the 8. So then you're going to have to take the 8th root on both sides. And when you take the 8th root on both sides, the 8th root on both sides means the radius here is going to be the 8th root of r instead of just r. So yeah, that's a tricky one. Write out the ratio test for that, and I think you'll get the result. Boy, this is a long one. This is taking a lot of time to go through. Let's see. If this is convergent, then that's convergent. Is that true? Oh my goodness. I'm having to really think about that one. My suspicion is, okay, so my suspicion is because 6 to the n is of greater, 6 is of greater absolute value than 2, we should have an easier time converging here with this smaller absolute value. Moreover, this is an alternating series, whereas this one is not. So I'm going to say true here because of the fact that this 6 is, right. View this as a power series. Okay, this is the easiest way to view. View as a power series, Cn x to the n. Well, if you just have x to the n here, this 6 is saying that a point 6 units from the center converges. Does a point 2 unit from the center converge? Yeah, for sure. Okay, so that's the way to think about it. This, though, is not necessarily true because, see, here we're an equal distance away from the center, and here we could be talking about endpoints. And as we've seen before, sometimes one endpoint is included and not the other. And so this is necessarily false because these are the same distance away from the center, and as a result, yeah, you might have one side being alternating, one side not, and then the one side converges and the other doesn't. Right, if this diverges when x equals 5, then it also diverges when x equals 9. That's true, right? Because when you talk about a radius of convergence, I like these last questions. These are actually pretty nice because this is a power series centered at 0. So if x equals 5 diverges, you know the radius of convergence is at most 5, which means the radius of convergence is clearly not 9. The radius of convergence is at most 5, which means anything further than 5 units away from the origin is going to diverge. That's the nature of a radius of convergence. Okay, that polishes off that. Let me stop this video because this one has gone on quite a while, but hey, it's good to go through. 100% chance power series are on the final, and it's good to have nailed down all of this discussion.